chemistry, we're going to begin a new unit today on acids and bases, and we'll start with the lesson Basic Acids and Bases. So acids and bases are important because they appear in many places in nature and in many everyday applications. For acids, these include fruits, foods such as fruits, citric acid, milk has lactic acid, vitamin C is actually called ascorbic acid, and many others. Industrial products, there's sulfuric acid in batteries, car batteries. Biological processes, such as the hydrochloric acid that's in your stomach to assist in the breakdown of food. Acids often have sour taste, so think about lemons, that's citric acid. So for bases, these include cleaning solutions, which include ammonia or sodium hydroxide, both are bases, and acids to neutralize stomach acids, such as Tums or Rolaids, biological purposes such as plant fertilizers. Bases are usually slippery and have a bitter taste. So think of soap. If you've ever gotten soap in your mouth, everybody has, it's very bitter, doesn't taste very good. So acids produce hydronium ions. This is the definition of an acid. This is what all acids have in common. They produce hydronium ions, and those can either be referred to as H+, that's a hydrogen atom without its electron, so it's basically just the proton nucleus, or H3O+. Now those look like two different things. H3O+ kind of looks like the formula for water with an extra proton, whereas H+ is just the proton. However, we treat those two designations as meaning exactly the same thing, and we'll talk about why. Bases produce hydroxide ions, OH-, and both of these do this in aqueous solution. Again, the only solvent we're ever going to talk about in this class is water. So you put these in water and these things happen. Bases are often referred to as alkaline. So if we look at an acid, it either produces an H+ or an H3O-, and we refer to either of those as a hydronium ion. So don't lose sight of that. Sometimes with all the discussions of acids, you can lose sight that what defines an acid is it produces a hydronium ion. And again, hydronium ion can be represented as either H+ or H3O+. Those are considered to be exactly the same thing. They're not two different things. For a base, they produce OH- ions, and those are called hydroxides. So just kind of take a mental picture of that and remember that what an acid is defined as, it produces hydronium ions in a aqueous or water solution, and bases produce hydroxide ions. So there are three definitions of acids and bases that are used in chemistry. The Arrhenius definition, first of all, the Arrhenius definition defines an acid as a proton, that's a hydronium ion. Again, think about that, H+. A hydrogen atom, a normal hydrogen atom, has a proton and an electron. One proton, one electron. Its atomic number is 1, so it has one proton. And when it's electrically neutral, it has one electron. If you're able to separate that proton and that electron from each other, then the proton by itself is a hydrogen ion, or we call it a hydronium ion. So it's the nucleus of the hydrogen, that proton, without its electron. So the Arrhenius definition defines an acid as a proton, that is hydronium ion, donor. It means it gives away a proton. And a base is as a substance that contains and releases hydroxide, OH- ions. Now there's another definition that was an improvement on the Arrhenius definition called the Bronsted-Lowry definition. Generally in high school and college chemistry, it's the Bronsted-Lowry definition we rely on in most cases. So the Bronsted-Lowry definition also defines an acid as a hydronium ion or proton donor. So it's exactly the same as Arrhenius. Base is where the two differ. In the Bronsted-Lowry definition, a base defines a base as a proton acceptor, necessarily, but something that accepts. It does it by accepting a proton. So the Lewis definition is one that's never talked about even in AP chemistry or freshman college chemistry, and that defines an acid as an electron pair donor and a base as an electron pair acceptor. Now, to scientist chemists, that's actually the broadest definition and the most thorough definition. However, it's never dealt with in college freshman and high school chemistry courses. So Bronsted-Lowry is the primary definition used on the AP exam and in introductory college chemistry courses. The Arrhenius definition of bases applies to strong bases. That is, a base is a hydroxide ion, releases a hydroxide ion. We'll talk about that in just a moment. So acids are substances that produce hydrogen ions called hydronium ions, H3O+. So there you see hydrochloric acid. That's the kind of acid that's in your stomach. So what has happened is a hydrogen atom with one proton and one electron has covalently bonded to a chlorine. So you see that the chlorine has a full octet, the hydrogen has a full octet. So that's just naturally what hydrochloric acid looks like. So hydrogen atoms consist of one proton and one electron and are electrically neutral. Often in natural chemical reactions, the proton is ripped away from a covalently bonded compound and leaves its electron behind. So watch what happens here. Remember in that bond right there between the hydrogen and the chlorine contributed one of those two electrons and the hydrogen contributed one of those two electrons, so they're sharing those two electrons. But there are times when that hydrogen is going to be more attracted to another atom, and we'll talk about that a little bit more in a moment. And so what happens is this. It gets pulled away. So notice what happened. The proton of the hydrogen got pulled away from the chlorine, but it left its electron behind. So that means the chlorine now has a -1 charge. And we've always said chlorine wants to have -1 charge. Just go to your charge number by ion sheet, and chlorine is a -1. And what it's produced over there on the right is a proton or a hydronium ion. So at this point, the proton becomes a hydronium ion. An Arrhenius acid and a Bronsted-Lowry acid are both defined as proton donors. Again, that word donor means they give away protons. So here's the chemical reaction for hydrochloric acid and water. You have HCl, you put it into liquid water, and what happens is that hydrogen, that H on the HCl, jumps over to the water molecule. And when it does, it becomes H3O+. Okay. Remember, an element is defined by the number of protons. So as long as you have the proton from the hydrogen atom, even if it doesn't have the electron, it's still considered to be a hydrogen. So if the proton from a hydrogen atom jumps over to the water molecule, instead of having 2 hydrogens, the water molecule now has 3 hydrogens, and it's no longer a water molecule, it becomes a hydronium ion. Then what's left behind with the hydrochloric acid is the chloride ion. And since the hydrogen left its electron behind, the chloride ion becomes negatively charged. So this reaction can be written using the H+ notation. Remember we said that the hydronium can either be written as H3O+ or H+ notation. So it would look like this. What you do is you simply use the abbreviation aqueous, meaning it's in water. You notice how the H2O doesn't appear in this. This is just a more abbreviated way of writing this. These two reactions are equivalent. And then instead of writing H3O+ on the right, you just write H+. And the Cl- remains the same. The HCl donates an H+ hydronium ion to the water molecule. Note that a strong acid reaction, and I haven't defined that yet, but this is called a strong acid reaction, such as HCl, is a one-way or irreversible reaction. Let me just quickly define that right now. A strong acid is one in which every single one of the acid molecules, the HCl's, gives up its proton to a water molecule. So you'll know that definition. You'll learn that definition in a later lesson. Okay. Once a proton dissociates, dissociate means breaks away from a strong acid, it never reverses and rejoins the conjugate base. And that's something that I don't know we're going to define in this class except right here. Cl- is the conjugate base of HCl, and I'll just define that later. So this is why the arrow points from left to right only. It is not a reversible reaction. You'll never have that proton jump back onto the Cl- and become a hydrochloric acid molecule ever again. Once that hydrogen leaves, it's never going to come back to the Cl-. That's the definition of a strong acid. So H plus and H3O plus mean exactly the same thing. So those two mean exactly the same thing. A lot of repetition in this lesson. H plus and H3O plus are both called hydronium ions. This seems tricky at first because H plus is just a proton while H3O plus is a proton attached to a water molecule. This is because an H plus in water does not simply float in the water solution. In the absence of a stronger base, the H plus ion immediately attaches to the water molecule. So it's going to immediately, if it's going to leave the hydrochloric acid, that proton, it's not just going to float around for a little while. It's going to immediately be pulled away by a water molecule and instantaneously attached to a water molecule to become an H3O plus. Here are a few more examples of Arrhenius and Bronsted-Lowry acids. So this is hydrochloric acid. And in the abbreviated notation where we just use H+, the HClO4 breaks into an H+ and the rest of it, which is the ClO4. But since that hydrogen atom left its electron behind on the ClO4, the ClO4 becomes negatively charged. I'm not going to get into the generics. That's when we get into some deeper analysis of acids, bases, such as in AP Chem, we talk about the generic notation. Here's another example. And now here's the same reaction, but it's written with the H3O plus symbolism for the hydronium. So you actually include water on the left side of the reaction, H2O. So that hydrogen on the HClO4 is going to jump over to the water molecule and turn the water molecule into an H3O plus or hydronium ion. And then this is nitric acid. There's the abbreviated notation where you don't include the water. And we're not going to deal with that. So an Arrhenius base is defined as a hydroxide OH- producer. So sodium hydroxide is what you used in the calorimetry experiment. It's a very strong base. So you'll notice something about its structure, NaOH. It actually has an OH. So if the Na and the OH break apart, which we know from our solubility rules, they always will in water, then the Na plus simply becomes an ion that floats around, and the OH minus becomes an ion in the solution also. So you have the Na plus the OH. According to the Arrhenius definition of a base, a compound must contain an OH minus that can be dissociated in water. So if you don't see the letters OH attached to a compound, it's definitely not an Arrhenius base. Now there are some compounds, in fact some acids, that you'll see OHs in. They're not bases, and that's a discussion for another day. But the ones you'll see here are going to be bases. Now a Bronsted-Lowry base is defined as a proton acceptor. So you'll notice that here the sodium hydroxide produced an OH minus without accepting a proton. Okay, so Bronsted-Lowry has a different definition. So here's an example of a Bronsted-Lowry base. So the Arrhenius base is a more direct way of producing a base. It just breaks apart and produces an OH minus in the solution. Remember, that's the definition of a base. It has to produce OH minus in solution. But look at Bronsted-Lowry. Arrhenius thought he had it solved as to what a base was, but then along came Bronsted-Lowry and some other scientists and said, wait a minute. We found out that NH3, which is ammonia, also produces hydroxides, OH minuses in water. And the scientists were perplexed by that for a while because they thought, well, NH3 doesn't have any OH attached to it. You don't see any OH in the NH3 formula. So how does it do that? And it does it kind of a sneaky way or a roundabout way. What it does is it's going to take one of the protons away from a water molecule. and that proton is going to jump from the water molecule over to the ammonia, over to the NH3, and turn it into NH4. It now has an extra proton, so it now becomes NH4. Since it has an extra proton, it's positively charged. And then by doing that, when you break a water molecule in two like that by pulling away a proton, you end up with OH minus in the solution. So it's kind of a backdoor way of getting hydroxides in the solution. So according to the Bronsted-Lowry definition of a base, the compound does not need to contain an OH minus. However, an OH minus must be produced, but how? Well, just explain that. In the example, the ammonia NH3 accepts an H plus, a proton, from a water molecule. This produces OH minus in the solution. That's a broken water molecule, even though the base NH3 did not contain an OH minus. So how a Bronsted-Lowry base reaction works. So there you start off with the NH3 and the H2O. So NH3 does not contain an OH minus hydroxide ion, but one is created when H2O donates a proton. Water acts as an acid in this case, because water is going to be donating a proton to the NH3. So there it goes. The proton jumped from the water molecule over to the NH3 to make it NH4. Plus the OH minus left behind that broken water molecule, it leaves a hydroxide in the water. NH3 accepts a proton and becomes an ammonium ion NH4+. So in this case, ammonia accepted a proton, was a proton acceptor. That makes it a base. And water was a proton donor. It gave up the proton to go over to NH3. That makes the water, in this case, an acid. In some reactions, water acts as an acid. In other reactions, it acts as a base. So here's a summary. In both the Arrhenius and Bronsted-Lowry definitions, an acid is a proton donor. This means it gives a proton away to water or another compound in solution. In the Arrhenius definition of a base, the base must be a compound containing OH minus that releases the hydroxide, the OH minus, into aqueous solution. This definition covers strong bases. In the Bronsted-Lowry definition of a base, the base must accept a proton from water or another compound to create OH minus hydroxide ions in solution. Anything that produces OH minus in solution is a Bronsted-Lowry base. The definition covers both strong and weak bases. All right, and that takes care of this introductory lesson on acids and bases.